And welcome back to our SPI Doppler Review series. Now that we've established the physics behind Doppler shift, we're ready, I'm trying to look at my head going this way, to examine how those frequency changes become the waveforms that we see on the screen. So in this episode, we focus on phase 5, spectral Doppler and signal processing. Again, where frequency shifts are transformed into visual spectrum using the fast Fourier transform. We'll break down how the spectral display is constructed, what the horizontal and vertical axis represent, and what features like spectral broadening actually indicate. So understanding this phase is essential because this is where interpretation happens. Doppler physics explains the shift, signal processing explains how that shift is displayed. So when you understand how the system converts raw frequency data into waveforms, the SPI questions about spectral analysis become much more logical. So let's move from measuring Doppler shifts to understanding how those shifts become diagnostic information. Now that we've worked through Doppler fundamentals, let's step back and look at the progression once again. So we began with fluid basics, understanding what blood is and what allows it to move. Then we explored flow types, identifying the different velocity patterns within a vessel. Next came the hemodynamics, where physics explained those patterns mathematically, connecting pressure, resistance, radius, and flow. After that, we entered the Doppler physics, where motion became frequency shifts. Then we examined the Doppler effect, the Doppler equation, and the critical role of angle. And today we're going to transition into the next phase, 5, the spectral Doppler and signal processing. So if Doppler physics explained how motion creates a frequency shift, signal processing explains how that shift becomes a visual waveform. So this is where the fast Fourier transform converts frequency data into spectral display, where time, velocity, amplitude are organized into something we can interpret clinically. So from here, we'll move into instrumentation, where machine controls influence how those signals are acquired and displayed. And finally, we'll reach the clinical application, where all of these principles come together in real diagnostic scenarios. So each phase builds on the one before it. And right now we're moving from understanding frequency shifts to understanding how those shifts become spectral tracings you analyze every day. So continuing with the same format, in this phase we're focusing on how Doppler shift or Doppler frequency shifts are converted into spectral display that you interpret clinically. We'll begin with the fast Fourier transform, or FFT, which is a mathematical algorithm, and we'll discuss what it actually derives, the Doppler spectrum. And this is the mathematical process that separates the complex frequency information into individual velocity components. Then we're going to clarify what the horizontal axis represents on the spectral display, time, and how that relates to the cardiac cycle and waveform repetition. From there, we'll examine spectral broadening, what it looks like and what it means, understanding vertical thickening of the tracing. That's critical for SPI interpretation questions. Finally, we'll discuss what can cause spectral broadening, including true flow disturbances and system-related factors such as beam spreading. Again, this section connects physics to visual interpretation, turning frequency data into meaningful diagnostic information. Okay, so let's look at the question. The fast Fourier transform derives a Doppler blank, and the options are A, color scale, B, spectrum, C, variance maps, or D, power display. And of course, the correct answer is B, spectrum. So remember, the fast Fourier transform derives the Doppler spectrum, and here's what that means. So the returning Doppler signal is a complex mixture of frequencies, and the FFT algorithm, this takes the time domain Doppler signal, it breaks it into its individual frequency components, and it displays those frequencies over time. So that output equals the spectral Doppler waveform. So without FFT, you wouldn't get the velocity versus time graph. Now let's look at why the other answers are wrong. The color scale. So color Doppler uses autocorrelation processing and mean frequency estimation. So it does not use FFT for the color scale. The other answer, C, variance maps. This is wrong because variance imaging also uses autocorrelation methods, not FFT. And the last answer, D, power display. Well, power Doppler measures amplitude or signal strength, again derived from autocorrelation processing, not FFT spectral decomposition. So if you see spectral Doppler waveform, velocity versus time display, or frequency distribution, think FFT. FFT equals builds the spectrum. Again, we're not going into detail on the fast Fourier transform. The whole point of this review is to review. Go back to your textbook and read more in detail about the fast Fourier transform. You don't have to derive it or anything for the SPI, but if you want to know more about its derivation, go back to your textbook or your instructor. Okay, the next question is, and again, the slide is very small, the horizontal presentation in the spectral display represents what? And the options are A, time, B, velocity, C, imaging depth, or D, acceleration time. And the correct answer here is answer A, time. So in a spectral Doppler display, the horizontal axis, the x-axis, is equivalent to time. The vertical axis, the y-axis, is equivalent to velocity or the frequency shift. So as the tracing moves from left to right, you're watching blood flow change over time. That's why you can measure systole, diastole, acceleration time, cardiac cycles, because the horizontal direction represents time progression. Now let's look at the other ones and see why they're wrong. So B says velocity. And velocity is plotted vertically. The height of the waveform above the baseline represents speed. So higher waveform equals higher velocity. C says imaging depth. And so depth is relevant in B mode and pulse Doppler sampling, but it is not displayed in the spectral tracing. And the last answer there was D, and that's also incorrect, acceleration time. Acceleration time is a measurement taken along the horizontal axis, but it is not what the axis represents. The axis represents time. Acceleration time is a derived measurement from it. So think of spectral Doppler like an ECG. Left to right equals time passing. Up and down is equal to strength and velocity. And then the horizontal is equivalent to time or equal to time. Okay, let's talk about the next question. Vertical thickening of the spectral tracing is called what? A, turbulence, B, range ambiguity, C, Doppler effect, or D, spectral broadening. I know we know the answer to this already, but let's go ahead and break it down. So the answer is D, spectral broadening, and that's a vertical thickening of the spectral tracing. Again, we call it spectral broadening. And so on a spectral Doppler display, the vertical axis is equal to velocity or frequency. The horizontal axis is equal to time. So when the waveform becomes thick vertically, that means there is a wide range of velocities present at the same moment in time. So instead of one clean velocity, you're seeing many different velocities layered together, and that widening is what we call spectral broadening. Now, why are the other answers incorrect? So A says turbulence. So turbulence can cause spectral broadening, but it is not the name of the waveform appearance itself. So turbulence is equal to chaotic flow. Spectral broadening is how that chaos appears on the tracing. So they're related, but not the same thing. The next one, B, says range ambiguity. So range ambiguity occurs in pulse Doppler. It happens when PRF is too high for the depth, and this causes incorrect depth assignment. It does not describe waveform thickening. And the last one is C, Doppler effect. So we know this, a Doppler effect, the phenomenon of frequency change due to motion. So it has nothing to do with waveform thickness. Now, if you think normal laminar flow, you'll see thin, clear spectral windows and sharp envelopes. Disturbed flow, you'll have window fills in waveform thickening and vertically, and broad range of velocities. And so that's spectral broadening. All right, moving right along. The next question, spectral broadening may be produced by what? Again, the answer is already highlighted there, but let's go through it anyway. A is low flow velocities. B says high wall filter settings. C is beam spreading in arrays. And D is low Doppler gain settings. So the correct answer here is C, the beam spreading in the arrays. Spectral broadening may be produced by beam spreading in the arrays, and here's why. So in spectral Doppler, each moving blood cell produces a Doppler frequency shift. Now, if all red blood cells are moving at nearly the same velocity, you get a narrow spectral tracing, like we said with plug flow. But if the ultrasound beam spreads or widens, especially with array transducers, the beam incinerates blood cells moving at slightly different angles. So different angles equals different cosine values. Different cosine values equal different Doppler shifts. So even if actual flow is uniform, the machine detects a range of frequencies, and that artificial widening equals spectral broadening. And this is called intrinsic spectral broadening because it's caused by beam geometry, not by turbulence. Now, why are the other answers incorrect? Why are they wrong, or why they're not the best answers? A says it's low flow velocities. So low flow velocities actually tend to produce narrower frequency ranges and cleaner spectral windows. Low flow does not inherently cause broadening. Answer B says high wall filter settings. So wall filter removes low frequency signals, if anything. A high wall filter may cut off low velocity components, but it does not create spectral thickening. And the last answer, D, was low Doppler gain setting. So low gain reduces signal intensity. High gain can make the tracing look thicker due to noise. But low gain does not produce spectral broadening. So two things to consider here, two main causes of spectral broadening. True flow disturbance or turbulence, and instrument-related factors like beam spreading. So this question is testing your knowledge of the second one.